Hello and welcome to Physics Lesson 3.07, Objects Launched at an Angle. This is part one of a part two lesson. We'll be doing two sample problems. So our problem reads, a football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. Calculate the maximum height, the time of travel before the football hits the ground, how far away it hits the ground, the velocity vector at the maximum height, and the acceleration vector at the maximum height. Well, if you remember when we talked about motion, so here's the ground, and we've got projectile, and we're going at 37 degrees. And we need to, start and stop from the same height. So that doesn't exactly look like the same height. Let me fix that. So for all these problems, we're assuming that we're starting and stopping from the same height, and we're going to make that height equal to 0. We have a velocity vector at an angle. So to start off with, our velocity vector, which we're going to call v sub o, this should be angle theta, has an angle. Now, that means that for this vector, and I'm going to redraw it, so let's do this initial, the initial. That means that this is going to have a component in the horizontal and a component in the vertical. So we're going to have Vx, we're going to have Vy. And just as we talked about for any of these problems, I'm going to try to focus this. I feel like I'm a little blurry here, a little blurrier than usual. We have to analyze this in two dimensions. We have to analyze the horizontal and we have to analyze the vertical. We can't do a combination. Vectors always have to be parallel and anti-parallel. The two motions have lives that are independent of each other. So we're going to have two separate vector banks. We're going to have a horizontal vector bank. And for this, we're only going to have three variables because what we learned was that all the way through the entire projectile motion, the horizontal velocity does not change. If my velocity is constant, then that means I have no acceleration and my original and final velocities are going to be the same. Then I'm going to have vertical. But for this, I do have changing velocity, so I'm going to have v sub o, y, v sub final y sub o, y sub f, a, and t. And we know that, let's go with a traditional coordinate system. I know that with a traditional coordinate system, this is going to be, my acceleration is always going to be down. And so in this case, down is going to be negative. So this is going to be negative 9.81. My initial y position is going to be 0. But what are these? This is going to be v sub y. I have to solve for these. So if I do, this is 20. So my initial velocity is 20. So if I do 20 cosine 37, that's going in a positive direction. This is going to be positive 20 sine 37. That's going to give me my values for here and here. And when I go to 20 cosine 37, I get 16 meters per second. And 20 sine 37 is 12 meters per second. You cannot put 20 into one of these values. This is a resultant value. And we have to put into the horizontal and the vertical values that are horizontal and vertical. All right, well, I've got some variables to get started. Let's start with letter A and see what it's asking me. Letter A says calculate the maximum height of the football. Well, that means I'm going to be solving for y sub f. So I have, boom, 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 three kinematic variables. Actually, no, I don't, because these all count for one. So I'm going to put a question mark here because that's what I'm solving for. The y sub o, y sub f stand for delta y, which is 1. But here, I could go to All right, sorry about that. I had to silence my phone. So we need a third kinematic variable. Well, if we're looking for the maximum height, we know that at the top of this flight path, in the vertical, this becomes 0. So for that split second at the top, that's 0. So now I have 3 kinematic variables that's going to let me solve for a fourth. And I think the easiest way to do that is going to be to use the v sub f squared equals v sub o squared plus 2a delta y. So that's going to become 0 is 12 squared plus 2, negative 9.81, y sub f minus y sub o, which is 0. And when I solve, I get a y sub f value of 7.34 meters. So my height here is 7.34 meters. All right, the next thing it asks for is the time of travel before the football hits the ground. Now we can do this a couple of different ways. Here we go, time of travel. Or the time of flight. I could plug in values here and solve for time, but keep in mind that that's going to be time for half of the flight. So whatever I use, if I use these variables to solve, the time I get here, I'm going to have to multiply it by 2. Well, what if I don't want to do for half? What if I want to solve for the whole thing? Remember, when we take off, so my starting vector looks like this. That's not really 37 degree. So I've got my Vx and I've got my V sub Oy. My ending vector is symmetrical. And so when I come in at the end, I'm going to have equal and opposite. This is going to be positive 20. This is going to be negative 20. They're going to be the exact same. Turns out the x component's going to be the same. This is going to be 16 and 16. This one was positive 12. Turns out this one will be negative 12 because projectile motion is symmetrical. So I can redo my vertical vector bank. Let's do this to v sub Oy, v sub final y. I'm just going to do a delta, or well, y sub O, y sub f, a, and t. This would be positive 12. This would be negative 12. This is negative 9.81. And I'm going to solve for time. These would be the 0 and the 7.35. But I can do v sub f equals v sub O plus at. When I plug in my values here, I get negative 12 equals positive 12 minus 9.81 t. And when I solve for t, I get 2.44 seconds. So why are these different than this? Remember, this is from, these values are from here to here. These values are from here to here. So it matters where in the, oh, I see I cut off again, darn it. Let me rewrite this. It matters where in my motion path I pick. So you can't just slap numbers in and think you're going to get an answer. You have to analyze where you're at on your flight path, what variables apply. All right, so for part C, how far away does it hit the ground? I can now take this value and bring it up to here because my time in the horizontal and my vertical are my linchpin. It links them together. I know the velocity is distance over time. So I'm going to have 16 is x over 2.44. And when I solve for x, I'm going to have 39.2 meters, I think. Now, there's another way you can solve for this, and it skips. Usually what you have to do if you want to solve for the distance traveled in the horizontal, by the way, this is called the range. The distance traveled in the horizontal. There's another formula that you can use, and it's called the range equation. The range equation says that the distance or the range is your initial velocity squared times the sine of 2 times theta over gravity. Now, the reason this is handy is because you can plug in your initial velocity here. So this is 20. So if I take 20 squared times the sine of 2 times 37 divided by 9.81, it's going to give me this. This is not on your formula sheet, but I always recommend to classes that they plug it into their calculators. Punch that into your calculator and keep it. And then you can do a really quick and easy range equation. So if it asks you for how the distance a projectile travels, and I should put a little asterisk here. We have to start and stop from the same height. We have to start and stop from the same height. All right, finally, for part D, it asks for the velocity vector at the maximum height and the acceleration vector at the maximum height. So let's go to part D. What color haven't I used yet? Let me grab purple. All right, so we want the max height. To find this answer, we have to talk about what's going on in the horizontal, what's Vx and what's Vy. So take a second and see if you can answer those questions. What's my vertical velocity at the top of the height path and what's my horizontal velocity at the top of the flight path? If you need to, pause the video here. Well, hopefully you said that at the top of the flight path, my horizontal is 0 and my vertical is constant. So whatever it was that I started with is what I've got now, and in this case, it's going to be 16. It's very common when you're asked what's the velocity vector at the maximum height for people to say 0 because they get used to this. But guys, that's in the vertical. You have a horizontal value too, so that means that your velocity at the top of the flight path, in this case, is going to be 16 meters per second in the horizontal. Well, okay, what about the vertical? I'm sorry, what about, not vertical, what about acceleration? Oh, we have to do the same thing. What's my vertical? What's my horizontal? Hopefully, let me go ahead and let me try to work on those. Give me an answer. Pause the video if you need to. Okay, hopefully you said that this is 0 because there's no acceleration in the horizontal because motion is constant. Hopefully here you said, assuming, well, we'll put negative 9.81 down. And in this case, it's going to be negative because of our coordinate system. So that means that my overall velocity, I'm sorry, acceleration is going to be negative 9.81 meters per second squared. 9.81. Okay, that is our first sample problem for objects launched in an angle. We'll do another one in part 2. So you can wrap it up here and head to part 2. Thanks for watching.